So the speaker today is Laura Munteanu. How you pronounce her name? She's a rising star in the community. She's also the product of the Ile-de-France educational system, it seems. She got her PhD 2 years ago in CEA, 2 years as a CERN fellow, and now already she got hard to get and hence very prestigious CERN LD 5-year position. So that's why she's smiling. You can ask her anything. You cannot bother her. She just found out that she got the position. She's all set. So I met Laura in January, I think. We bonded on 2 things. One, because we had Pierre is our postdoc in group. They share the same
master's and PhD.
Master and PhD, and the PhD advisor was the same, and we also speak the same language. We are Romanian, so well, we speak Romanian. We're okay. So I let her talk about the neutrinos and the neutrinos.
Thank you very much, Camilla, for this introduction, and thank you very much for hosting me here today. I'd like to talk to you about neutrinos and generally provide some ideas on the path towards precision measurements of neutrino oscillations with future experiments. So neutrinos are the most abundant massive particle in the universe, and they come from a variety of both natural and man-made sources. And they also span, as you can see from this plot, a very wide range of energies. Because they span such a wide range of energies and they have very different properties, there's also a wide range of experiments which try to probe neutrinos and their properties. And because these are so many experiments, I'm actually not going to be able to talk about all of them, but I would like to concentrate on what we can learn from accelerator-based neutrino oscillation experiments. But before I do that, I'd first like to start with a brief introduction to neutrino oscillations. This is probably going to be familiar, so I won't spend too much time on it. So as you all know, neutrinos are the only particles in the standard model which interact exclusively via the weak interaction. And when they are created, they are produced in a particular flavor eigenstate. If we have a charge current interaction in particular, then we have a neutrino which is of the same lepton flavor as the lepton that is also produced in this interaction. So by looking at charge current interactions, we can tag neutrinos by their flavors. Now, this is the production mechanism. However, in the 2015 Nobel Prize was awarded for the discovery of neutrino oscillations, which proves that neutrinos have mass. And a consequence of the fact that neutrinos have mass is the fact that their flavor eigenstates are different from the mass eigenstates. And one of the ways in which we can relate the two is via this unitary mixing matrix, which is called the PMNS mixing matrix. And in this case, we assume it is unitary and that we only have 3 neutrino flavors. So the flavor eigenstates are different from the mass eigenstates, which also means that a neutrino produced in a particular flavor eigenstate, a mu over here, will then have different mass eigenstates that make up its composition. And each of these individual mass eigenstates, because they have different masses, will evolve at a different rate in time. So you can see we get a time-dependent phase, which depends on the neutrino energy, and this will be different for all the mass, for the different masses that make up this flavor eigenstate. Now, then when we interact, or effectively when we detect the neutrino, we also detect it via weak interaction, which means we again move to the flavor basis. So we then make it collapse into a perhaps different flavor eigenstate from the one in which was originally produced. And this is known as neutrino oscillations. So you can see there's a certain probability of a neutrino produced in a flavor alpha to be detected in a flavor beta. And this depends on the terms of this matrix, but also on the neutrino mass and the neutrino energy. We can learn many things from neutrino oscillations. I'd like to highlight a few of the features that we can extract from these phenomena by illustrating how the oscillation probability changes based on different parameters. So first and foremost, the neutrino oscillation probability depends on the neutrino energy itself. This is the probability of muon neutrino disappearance or the survival of muon neutrinos. And you can see it evolves as a function of the neutrino energy. The oscillation probability also depends on how long or for what distance the neutrinos oscillate, which is known as the oscillation path length or the baseline. And you can see how different the probability is for different so-called long baseline experiments, such as T2K, NOvA, and in the future, the Dune experiment. The oscillation probability also depends on the mass difference between the neutrino mass eigenstates. With certain type of experiments, we only have access not to the absolute neutrino masses, but rather to the difference between the mass squareds of the different types of neutrinos. And you can see that changing the so-called mass splitting over here will have the effect of shifting the oscillation probability horizontally along the energy axis. And one of the main unknowns in neutrino physics is exactly what the neutrino mass ordering is. So we know that they have masses. We know that we can access their mass splittings, but we don't know if the largest mass splitting is here or here between these two states. And this is what's known as the mass ordering problem. We don't know if they follow the same ordering as their charged lepton counterparts or an inverted mass ordering. The oscillation probability also depends on the actual parameters of the mixing matrix. The mixing matrix can be parameterized as a product of 3 rotation matrices. And here I've highlighted the different experiments which have the best sensitivity to measuring the parameters of each of these rotation matrices. And here I can show one example in which we vary one of the parameters, one of the mixing angles, theta 2,3, and we can see that the effect that it has is to shift the depth of this oscillation tip. Now, because this is also a complex matrix, it doesn't have to be real. There's one parameter that I'd like to highlight in particular, which is the CP-violating phase, or the Dirac CP-violating phase, delta CP, which appears here in this middle matrix. And this time I'm showing not muon neutrino disappearance, but rather electron neutrino appearance. And you can see that depending on the value of this phase, we can have different probabilities or different event rates that we can actually measure in our experiments. And this also depends on what assumptions we make on the mass ordering. So this can shed light into one of the most fundamental questions that we're trying to answer right now in particle physics, whether there is a new source of CP violation in the lepton sector, which we can probe through neutrinos. And finally, we don't just want to have an idea of the values of these parameters, but we'd like to determine them precisely so that we can see if they can inform us about underlying symmetries. You can contrast this with the mixing in the quark sector. You can see this is so the analogous type of mixing that happens in the quark sector. You can compare the size of the different terms of these matrices, and you can see that the quark matrix is basically diagonal, whereas this is not the case for the neutrino matrix. And we want to see the precise values of the parameters, first of all, to see if PM&S is all there is, but also to see if there are any other, if there's any feed downs from higher energy, higher order theories that might point to some underlying symmetries in this mixing. But so how do we measure neutrino oscillations in practice? I'm going to focus on the example of long baseline oscillation experiments because I think they are the ones which allow us to probe multiple parameters, the most parameters at once, and give us a very comprehensive view to a lot of these questions. So we usually start with producing an artificial man-made neutrino beam. This is a high purity and high intensity muon neutrino or anti-neutrino beam, and it is produced usually at an accelerator complex by impinging protons onto a graphite target. Then the protons which interact with the graphite will produce mesons such as pions or kaons, which will then decay, and in their decays produce muons and muon neutrinos or anti-neutrinos. We can stop the muons by using a beam dump, and then we end up with a beam composed primarily of neutrinos. Then the composition of the beam is measured almost immediately or at a very short distance after the production point in order to see what the spectrum looks like before oscillations. And this is done with a near detector complex, which measures the spectrum before oscillations. This is an example of such a spectrum, of such a flux for the T2K experiment. So it's peaked at around 600 MeV, and it is composed of only one neutrino flavor. Then the beam is left to oscillate for a certain distance, which is known as the baseline. It is about 300 kilometers in the case of the T2K experiment. And we can optimize the design of both our beam and our baseline in order to maximize our sensitivity to what we're looking for. In particular, we can choose a suitable value for the ratio of the baseline L over the energy E in order to maximize, as you can see here, the muon neutrino disappearance probability and enhance and maximize the electron neutrino appearance probability. We can play further tricks, and T2K notably uses the so-called off-axis technique, which means that it directs its neutrino beam at a slightly off-axis angle from the far detector, which I'll describe in a moment, with the aim of peaking the spectrum even more than it would have been if it were on axis at this oscillation maximum, and this also helps reduce the intrinsic electron neutrino contamination. Finally, we measure the composition of the flavor modified spectrum with the far detector this time. And you can see how our initial muon neutrino spectrum now is dominated by tau neutrinos and electron neutrinos over here, which have appeared. And by looking at these event rates, we can infer the oscillation parameters. There are two operating long baseline neutrino oscillation experiments today. These are the T2K and the NOvA experiment, and I'll talk later about the future mega projects, Hyper-K and Dune. But what I wanted to illustrate is that the experiments that we have today and that we'll have in the future span a wide range of energies, have different baselines, therefore have different sensitivities, and also use different detector technologies, sometimes different between both their near and the far detectors. And in the following, I'm going to concentrate on the example of the T2K experiment, but most of these concepts can be applied to any long baseline experiment. In order to actually get the oscillation parameters, we measured them by comparing the observed event rates at the near and at the far detectors. There are several contributions to this event rate. So we have, of course, the oscillation parameter. So we'll begin with the neutrino flux, which tells us how many neutrinos were actually produced. Then the interaction cross-section, which tells us how many of the produced neutrinos interacted in our detector. And then the detection efficiency, which tells us how many of the interacted neutrinos we were able to detect. This part is in principle to some extent common between the near and the far detector, but at the far detector, we have an additional term, which is the oscillation probability, which is negligible at the near detector, and this contains our parameters of interest. Because we measure the event rate and not directly the oscillation probability as a function of the neutrino energy, a precise knowledge of all of these terms is required in order not to bias our measurements. And this is what we call sources of systematic or nuisance parameters, which we need to control. Because at our near detector, the oscillations are negligible, and also we have a much higher event rate than at our far detector, we can use the near detector data to obtain an independent constraint on these sources of systematic parameters. The story is in reality a bit more complicated because this is not just a simple product, because otherwise everything would just cancel and it would all be very simple. In reality, what we do is we try to infer the oscillation probability as a function of the true neutrino energy, but what we measure is a reconstructed neutrino energy, and therefore we rely on a precise knowledge of the mapping between the true and the reconstructed neutrino energy, which is our energy smearing matrix. And we also rely on a robust extrapolation model between the near and the far detector, because these differences don't just cancel out between the two. At T2K energies and at Dune energies as well, so at the scale of 1 GeV energies, neutrinos mostly interact with atomic nuclei. They interact via both neutral current and charged current interactions, but we target the charged current interactions because they are the ones which allow us to tag the flavor of the neutrino and therefore study flavor oscillations. You can see here an example of the unoscillated flux and the oscillated flux at T2K and the rate of the different processes. The dominant channel that we have is the so-called CCQE, or charged current quasi-elastic process, in which a muon neutrino interacts, in this case, off a neutron to produce a muon and a proton in a final state. But we also have contributions from higher energy interactions, such as two-particle to hole interactions, in which the neutrino interacts off a correlated pair of nucleons inside the nucleus. We have resonant interactions in which the nucleon is excited to a delta baryon, which then decays, producing pions and other nucleons, and also deep inelastic scatters at higher energies in which we produce hadron jets, and so we have a higher multiplicity of hadrons in the final state. Now, if this is our dominant channel, the process that T2K uses, the method that T2K uses to estimate the incoming neutrino energy is to assume that all of our interactions follow this type of diagram. And this is a deceptively simple diagram because it's just a two-body interaction. So in principle, just by measuring the properties of the outgoing muon, we can infer the energy of the incoming neutrino. And this is also done because our far detector, which I'll describe a bit later, can mostly detect charged leptons. So we've optimized the near detector for us to do the same. However, in reality, this is not a simple two-body scatter because the nucleons that the neutrinos scatter off are bound inside complex nuclei and are therefore subjected to a number of nuclear effects. The first of these is the Fermi motion, or the fact that nucleons are agitated and they're moving inside the nucleus, and they're also bound with a certain energy. And this is something that we don't take into account into our formula. In addition to that, there's a more complex nuclear optical potential, which needs to be taken into consideration for the full computation of this diagram. We can also have correlations, which already exist between the nucleons, and even the proton that we produce in our final state won't necessarily make it out of the nucleus unscathed, but can undergo subsequent reinteractions inside the nuclear medium in what is known as final state interactions. And these can bias the interaction topologies that we then look for in our detectors. So the impact of nuclear effects is quite large. You can see an example here of what the oscillated spectrum looks like in the solid blue line, assuming that it is drawn as a function of true neutrino energy. And when we draw it as a function of reconstructed energy, it looks completely different. So it has a very big effect on the actual event rates that we measure. It's fine that it doesn't look the same as the true neutrino energy, but what matters is that we know exactly what this mapping is. And this is not the state at which we are today. So at T2K, we then use our near detector at 280 meters to characterize the flux, the event rate before oscillations. The ND280 detector is a magnetized detector. We use the UA1 magnet yoke, which allows us to separate charged particles by their charge and therefore perform better particle identification. It uses a series of electromagnetic calorimeters to surround this tracker portion. This is the incoming neutrino beam, and the interactions will take place here. And then the neutrinos themselves will interact in these two targets, which are made of plastic scintillator of this type. I can pass this around. So this is I think from the Minos detector, a bar of plastic scintillator, which are quite thin, but also very long, and we have a grid of these. And then later on, we also have another target, which also has plastic bags, which also has bags of water in order to match the target that we have at the far detector. And finally, the two targets are surrounded by three time projection chambers, or TPCs, to track the outgoing particles and perform PID. In order to obtain our near detector tune, we then perform a fit to the near detector data. This is actually a simultaneous fit of about 20 samples, some dominated by the signal processes, some to constrain the backgrounds. And it's in reality a two-dimensional, so each of these samples is binned in 2 dimensions as a function of the outgoing muon kinematics to sample the full interaction phase space. But here I'm presenting just an example of this projection onto 1 dimension, which is the muon momentum. And you can see what the agreement between the data and the Monte Carlo looks like before we perform the near detector fit. You can see that there's clearly an enhancement needed to the Monte Carlo that we've used. Once we performed this fit, in which we vary the parameters related to the flux detector and especially to the cross-section model, we then improve significantly our agreement between the data and the Monte Carlo in what is known as the near detector tune. But this goes further than just improving the agreement between the data and the Monte Carlo. Before we perform the fit, we have a series of parameters that describe our flux, our detector model, and our cross-section systematics. And initially, we assume no degree of knowledge or of correlation between these different parameter categories. Once we perform the fit, we can see that we have these new correlations which appear between these different parameter categories, which help us both better constrain our uncertainties, but equally bring with it the challenge that we need to parameterize our uncertainties in a way that allows our data to disentangle them from one another. So once you've performed this fit, we then move on to performing the second step of the analysis, which is fitting the data at the far detector. The far detector at T2K is the super Kamiokande detector, which is made of 50 kilotons of ultra pure water. The inside of the detector is surrounded by 11,000 photomultiplier tubes. And the way in which it works is to detect charged leptons through Cherenkov radiation. So the charged leptons above threshold will emit Cherenkov rings, and then we can see them through the PMTs. And what we care about is especially distinguishing events that occurred in interaction of a muon neutrino from those of an electron neutrino, which would appear in the beam. You can see a muon ring has very sharp edges like this, whereas an electron ring has fuzzier edges due to the multiple scatterings that electrons undergo in water. So now, once we've obtained our near detector fit, we can say with some degree of confidence that we know what our flux, our cross-section, and our detector model should look like. So we assume that the remaining discrepancy between the Monte Carlo and the data will be due to oscillations. So these two spectra over here show the simulation for the muon neutrino disappearance spectrum and the electron neutrino appearance spectrum as a function of the neutrino energy. And the different bars show the size of the systematic uncertainties before the near detector fit in blue and after the near detector fit in red. You can see that before the near detector fit, we were about 15% of systematic uncertainties. And this has been reduced. And from these, the dominant source of systematic uncertainties comes from cross-section uncertainties. And after the near detector fit, they have been reduced to the order of 3 to 4% across the main signal samples. And moreover, you might also notice that in addition to this, the shape of the spectrum has also been modified. And this is directly driven by the data at the near detector. But even after this adjustment, the dominant source still stems from our parametrization, our modeling or lack of knowledge of neutrino-nucleus interactions. I'd like to just briefly present the most recent results that we have from the T2K experiment, which has the leading constraints on some of these parameters. So on the muon neutrino disappearance channels, in which we see how many of the produced muon neutrinos have survived, we have a really good sensitivity to the so-called atmospheric sector parameters, which are theta 2,3 and delta and the mass splitting delta m square 3,2. Here we can see the different confidence intervals that T2K obtains for these parameters, assuming both normal ordering and inverted ordering. And what T2K has today is that it seems that the best fit value for sine square theta 2,3 lies in the so-called upper octant. The upper octant is we refer to it as an octant because as an angle, it can be written on a circle, and you can divide that circle into 8 bits. And it could be either in the first octant or the second octant, or exactly in the middle, which would imply there's a maximal amount of muon neutrino disappearance. We don't exclude the lower octant yet, and the data seems to have a very weak preference for normal ordering. T2K currently has the world-leading constraint on the atmospheric parameter oscillation, on the atmospheric oscillation parameters. You can see this is the T2K result over here compared to the ones from NOvA, from IceCube, and from SuperK. On the appearance channel, we study electron neutrino appearance and anti-electron neutrino appearance in a beam of muon neutrinos or anti-muon neutrinos. And here we can look at the difference between electron neutrino appearance and anti-electron appearance and compare it with the different values of delta CP. With the predictions of different values of delta CP. What T2K sees is that we see a preference for values of sine delta CP below 0. So this shows the delta chi-square as a function of delta CP for normal and inverted ordering, and the confidence intervals at different degrees of confidence level. And what we have today is that CP conserving values of 0 and pi are outside of our 90% confidence level. We can contrast this with what the NOvA experiment sees, in which they seem to prefer values of sine delta CP above 0, assuming that the ordering is normal. But even so, you can see that the two contours overlaid here. So this is T2K in blue and NOvA in red. And in normal ordering, they seem to sort of disagree, but in reality, it's not a statistically significant tension. And in inverted ordering, there's quite good agreement between these experiments. So the obvious question to ask is, how can we do better? How can we improve these results and actually say something about CP violation in the lepton sector? Well, the obvious answer is to accumulate more data. And we can do this also by taking more data with our current experiments, but we can already begin improving our results by combining the existing data between the existing experiments. Both T2K and NOvA are statistically limited, but by putting their data together, we can hope to gain something from each of these experiments to advance their common cause. This is particularly interesting for these experiments because they have different neutrino energies. NOvA has a wider neutrino energy flux than the T2K. NOvA also has a much longer baseline, which means that it is more sensitive to the mass ordering, which T2K is less sensitive to, but T2K can contribute to better sensitivity to the delta CP phase. And this joint fit is now underway, and hopefully in a few months, we will find out the results of this joint fit. I'm also happy to say that we have had the first joint data fit between two neutrino experiments with the example of the T2K plus SK atmospherics joint fit, in which we combined the information, the data taken with the T2K neutrino beam and the atmospheric neutrino oscillations from Super Kamiokande. You can see an example here of the sensitivity to delta CP and to sine square theta 2,3 from the Super K experiment, and you can see that it's quite low. And then if you compare this to the blue line, which comes from T2K, you can see that the result of the joint fit is mainly driven by T2K on the delta CP front because of its enhanced sensitivity. But Super K also brings something to the table as well. This is the other parameter. This is another parameter, so theta 2,3, and you can see that T2K on its own seems to prefer the upper octant, SK on its own seems to prefer the lower octant, and together there is no more clear octant preference between the two experiments. And the advantage of this fit is that in addition to just combining the statistical likelihoods, it also combines the full systematic error models of these two experiments, which is a first in this field. Of course, in order to take more data, different experiments are planning upgrades to their experimental configurations, and T2K plans a new data taking phase, which has just begun last month. It's called the T2K2 phase, in which it will increase its beam intensity from about 500 kilowatts today up to 1.3 megawatt towards the Hyperkamiokande era, which will begin in 2027. Because we're going to have more intense beams, we also need better detectors in order to resolve the new data in finer detail. And some of the main actors on this front will be liquid argon TPCs, which are sometimes referred to, and I like this comparison, these are colored bubble chambers, so they give you a very precise picture of the tracks, but also more information about the charge deposits. But equally, there's this new scintillator cube technology, of which I brought a tiny cube here. So these are the same sort of plastic scintillators that are used in T2K today, but in the form of very small 1 centimeter wide cubes, which offers very high granularity. And in addition to that, once we have more data and we can resolve better, we also need to improve our treatment of systematic errors in order to build robust analyses. An example of what can happen if we don't properly take into account the modeling of nuclear effects onto our analyses is this example here, where we simulate a series of oscillation parameters. So this is the correct result, which we should have obtained. And you can see what type of bias we could get into the oscillation in the measurement of oscillation parameters if we don't account, in this case, for some effects related to hadron transport through the nucleus. So what does the future look like? The future in long baseline experiments, it will be dominated by the mega projects DUNE and Hyperkamiokande. When I say that these are big projects, I actually mean big because each of the DUNE 4 far detector modules is about the size of a long-haul airplane, and Hyper-K is about 1.5 airplanes. So they are very big and very costly. They're very ambitious, and they have also comprehensive physics programs, which start with neutrino oscillations, but will also contain insights into beyond a standard model physics, and supernova neutrinos and many other topics. But their first short-term goals include notably determining whether CP symmetry is violated in neutrino oscillations. On the mid to long-term scale, these will operate for 20 years or more. These include precision measurements of oscillation parameters, and the two experiments are very different and as a result, very complementary and not just competing with each other. Are we prepared for future experiments? Well, to give you an idea of this, we can look at the number of events that T2K and NOvA, the leading experiments in this field, have accumulated for the last 10 years. And you can see in the dominant signal channels, we have about 300 events for T2K, and in the dominant muon samples, we have about 300 events for T2K, and about 100 or even less in the anti-electron neutrino channels for T2K. So after 10 years of taking data. I can let you work out the square root of n in your head, but you can compare this to the size of the systematic errors that we have right now, and we can clearly see that we are statistics dominated at this level. For future experiments, Hyper-K and DUNE, the same channels will collect about 50 times more data, and this will begin very, very early on as soon as they begin taking data. And you can see that we'll reduce our statistical errors by about an order of magnitude. Now, are we prepared with our current systematic errors? The result is no, and I wanted the answer is no, and I wanted to show you an example of what this could do to our future experiments. If we take the example of the Hyper-K experiment, you can see the Hyper-K sensitivity to exclude CP conserving values for delta CP as a function of Hyperkamiokande data taking at 3 sigma and at 5 sigma level. And the different lines correspond to different systematic error scenarios. The solid line over here only has only takes statistics into account. So it's as if we mastered our systematics completely. And then the difference between these two lines is the finely dashed one shows T2K level systematics, so about 5%. And the coarsely dashed line shows an improvement in some of the key systematics for delta CP measurement. And if you project the difference between these two lines onto the x-axis, you can see that this can make a difference of about 5 years in the discovery of CP violation. And for some other goals, which include precision measurements at a certain target precision, these results can be delayed altogether for these future experiments. So we need to reach, we need a dedicated and focused effort in order for future experiments not to be prematurely limited by systematics. The culprit is, of course, the systematics related to the interactions between neutrinos and nuclei. And this is the case for T2K, where this is the dominant source of systematic uncertainty. This is also the case for NOvA, the dominant source on the electron neutrino event rate. And therefore, we should ask ourselves, are we prepared right now with the models that we have? So our models perform quite poorly right now, and there are many ways to illustrate this, but I've chosen an example in which we see the same variable, so the same observable, which is the transverse momentum imbalance between an outgoing proton and an outgoing muon. So this is the same variable measured by different experiments, microboon, T2K, NOvA, and an electron scattering experiment. So this is done by the E4Nu collaboration. All of these experiments operate with different detectors at different energies, measure the same observable. And the other thing that all of them have in common is that if you look at the agreement, at the ratio between the chi-squareds and the number of degrees of freedom, you can see that no model is able to describe global neutrino scattering measurements in their entirety. So this can be a bit disheartening, but in reality, it should actually be used more as an opportunity to learn better about where we don't actually model things well and to target our efforts a bit better. So what exactly do we not know about neutrino interactions? Well, there are certain things that we know we don't model well. We deliberately chose to ignore them sometimes in our simulations, or they're very hard to implement. And sometimes that's fine at the current level of statistics. This is a non-exhaustive list of things that we know we could improve, notably hadron transport inside the nucleus, or differences or how different nuclear effects scale with atomic target. But there are also different effects that we don't know. So this is a source of unknown unknowns. But the silver lining here is that previous unknown unknowns can become known unknowns. And to give you an example of how this happened, there was the so-called mini-boon axial mass puzzle, in which the mini-boon experiment measured, so the data showed a large discrepancy with the Monte Carlo, and one way in which this could be fixed was by increasing drastically the size of the axial mass, which was in stark disagreement with bubble chamber measurements. Fortunately, in the nuclear physics community, they were aware at the time even of the existence of so-called multinucleon interactions or correlations between pairs of nucleons. And this was previously in effect neglected in the neutrino physics community. And once this, as well as another effect related to the nuclear potential or to the nuclear screening, has been included into our analyses, we've been able to reproduce the data. And one previous unknown unknown therefore became a known unknown, and now we account for it properly into our analyses. Why does all of this matter? Of course, ultimately, what we want to reach isn't just a good understanding of nuclei, but what we want to measure the actual oscillation parameters. And what systematics matter for different oscillation measurements, it depends on what we're trying to get out of it. So for instance, the main challenge for excluding CP conservation stems from differences related to the interactions between the ways in which electron neutrinos and muon neutrinos interact. Now you'd say lepton universality, in principle, it shouldn't be that different. However, when you interact with atomic nuclei and you produce via charge current interactions a charged electron or a muon in a final state, there is a mass difference. And this can matter more or less depending on what regions of phase space we live in. And to give you an idea of how this impacts experiments, this is the hyper-K sensitivity to exclude CP conservation as a function of the true value of delta CP. And you can see that about half of the systematic error budget over here stems from exactly these types of effects. Our current constraints are mainly driven by theory, but again, the silver lining is that there are prospects to significantly reduce the impact of theoretical uncertainties on the modeling of these effects. More importantly, maybe than this, there are other challenges for precision measurements, and these are the real long-term goals of these experiments. And I'd like to illustrate here how the main contributors to precision measurements are related to our precision in reconstructing the neutrino energy, or the shape of the oscillated spectrum. This is true for both hyper-K and for Dune. So for hyper-K, here you can see an example of the ratio between the electron neutrino appearance spectrum to itself, so to the nominal spectrum. This is just a line at 1. And then we can compare this with two types of shifts. The blue line represents a shift of 0.5% in the neutrino energy scale, and the pink line represents a 12-degree shift in delta CP, which is the target precision on delta CP. And what you can see is that these two effects are degenerate even in the electron neutrino spectrum. Similarly for Dune, you can see an example of what happens if we don't account properly for about, in this case, 20% of the visible energy that goes into protons, and we assume that it goes into neutrons, which we don't see with these detectors. And you can see that we can simulate values of oscillation parameters that would be here, and what we measure in our analyses would be severely displaced with respect to what we put inside. So in order to understand how we can improve our modeling of neutrino energy reconstruction, it's worth looking at the differences between these different types of experiments. So, of course, the challenges for Hyper-K and Dune are different because they use different detectors and therefore use different detection techniques. Hyper-K uses the water Cherenkov technique, so it measures the kinematics of the particles above threshold. It's not a magnetized detector, so we can only see the rings, whereas Dune is more of these like colored bubble chambers, so liquid argon TPCs. They see almost the entire full final state as well as the energy deposits. Because we have different detectors, we therefore use different reconstruction methods for the neutrino energy. At Hyper-K, we use the so-called kinematic energy reconstruction, which I previously described, in which we only measure the muon and infer the neutrino energy from the lepton kinematics under this two-body interaction assumption. Whereas for Dune, we add up all of the visible energy from the final state particles. This means that we can see the energy from the muon, from pi zeros, which decay into photons, from protons, but it also importantly means that we do not see the energy from neutral particles such as neutrons. And therefore, this has different effects on the way in which this biases our neutrino energy reconstruction. These two plots show the same quantity, the relative bias on the neutrino energy reconstruction for Hyper-K and Dune. And you can see that it has a very different shape because there are different contributions to it. At Hyper-K energies, most of the spread here is dominated by these so-called CCQ interactions, where it stems from our neglect, from the fact that we neglect the movement of the nucleons inside the nucleus and the energy with which they are bound. In addition, we have some contributions from other higher energy interactions, and notably related to pion transport through the nucleus. For Dune, on the other hand, you can see that the intrinsic bias itself is very small. So the fact that we're at zero means we don't have a bias. However, there is a bias on this side of the distribution, and there are two main contributors to it. One of them are pion production processes. So this is the small peak over here, if we assume that we don't correctly count the numbers of pions that we have. And the second one is this contribution, which comes from events with neutrons, which, as you can see, dominates the neutrino energy bias. And on the Hyper-K side, it's true that the intrinsic smearing is wider, but the good news is that it's also easier to control. There have been more than 10 years of neutrino experiments which have been measuring exactly these types of processes, which will allow us to correct for this bias. Whereas on the Dune side, the smaller intrinsic smearing, the intrinsic smearing is smaller, but it is also harder to control because there haven't been many measurements that measure exactly these types of interactions. To some extent, it doesn't, as I said before, it doesn't matter that there is a bias. It matters that we know exactly how to map back from it and that there's little uncertainty on that. And for Dune, the situation is that if we compare all of the models, most of the models available in our neutrino nucleus, in our neutrino interaction generators, you can see the high disagreement between these different models, especially in the tails of this distribution. So we need really to narrow this down because this is at a level unacceptable for the Dune precision goals. However, the future of neutrino cross-sections is bright, and there are ways in which, and there are prospects to improve these measurements. I'd like to cite a few of the ongoing efforts, which we look forward to in the coming years. One of them is, of course, the SBN, or Short Baseline Program at Fermilab, originally designed to look for sterile neutrinos, or to infer or to confirm the mini-Boone excess problem, but which have their own cross-section measurement programs on their own. The SBND, or the Short Baseline Near Detector in particular, will use the BNB beam from Fermilab and will produce the highest statistic measurements on liquid argon, thousands of neutrino events per day on liquid argon at lower energies, however, compared to the Dune spectrum. On the other hand, we also have the Icarus detector, which is sitting slightly farther away from the BNB beam, but we'll also see neutrinos coming from another beamline at Fermilab, which is the NUMI beam. And there it will use the same sort of trick as T2K and look at it from an off-axis angle. And as a result, it will have fewer events. But this time, if you look at the neutrino energies that these span, you will see that there are much higher energies and better match the phase space of Dune. In addition to this, there is a demonstrator module, so-called the 2x2 with the argon cube demonstrator for the near detector for the future Dune near detector. And this is currently being exposed to the NUMI beam at Fermilab. And what you can see is that if we plot here a variable which is relevant, which is called the invariant hadronic mass, the invariant mass of the hadronic system, you can see that the type of phase space that we see in these in the interactions in this detector will match really well the one that we see in Dune, albeit with lower statistics. In addition to this, there are not only liquid argon detectors in the neutrino in the future of neutrino physics. One main actor here will be the T2K experiment with its upgraded near detector using these very small scintillator cubes. The near detector upgrade will consist in replacing this upstream part of the detector with a new target, which will be made of these scintillator cubes, and two new time projection chambers. And here is the same observable that I showed a couple of slides before, which has now been measured by many of the existing experiments and all rule out a lot of the existing models. What you can see here is that if you compare the size of these error bars that we will be able to obtain with the new T2K beamline and the new detector capabilities, then this will clearly allow us to distinguish between all of the models that we have currently on the market. But there's more to this, and one very important characteristic of this new T2K near detector is that it has something unmatched in the neutrino community, which is the fact that these small cubes will allow it to detect neutrons. Neutron detection, as I said, so neutrons are very important for Dune because they will not, liquid argon TPCs cannot see neutrons in the final state. It's basically invisible energy. And the way in which we can detect neutrons with these small cubes is the following. If we have here an anti-muon neutrino, which interacts at the vertex, produces a muon, the muon will deposit some energy in the cubes. And then later on, because of its very precise timing resolution, which is of the order of 1 nanosecond, later on, the neutron itself won't deposit energy, but will knock out a proton, which will deposit energy in a few very small cubes near this interaction vertex, the secondary vertex. And then by looking at the difference in the time of flight between these 2 points, we can we can determine on an event-by-event basis the kinetic energy of the neutron in these interactions. And this can be used not just to measure states with interactions with neutrons in the final state, but can also allow us to measure interactions completely devoid of nuclear effects. And the way we can do this with the plastic scintillator target at T2K, so it's made of hydrocarbon, and the key word here is hydro, because it's carbon and hydrogen. A hydrogen atom, by definition, is a free proton, so it's by definition free of nuclear effects. So if you can isolate a sample enriched in hydrogen interactions, we can get rid of many of these nuisance effects related to neutrino-nucleus interactions and obtain precise flux measurements in situ, but also measurements of, for instance, nucleon level quantities such as the axial mass form factor. The first time, so we've developed a method to do this by exploiting actually the same variable that was shown previously, which is the transverse momentum imbalance. And you can see that for a hydrogen atom, so for interactions of hydrogen, we have very low values. So this distribution peaks here at very low values of this quantity. Whereas for carbon atoms, this has a more smeared out distribution towards higher values. And by placing an appropriate cut, we can isolate a sample which is enriched in interactions on hydrogen. To give you an example of how well this works, the Minerva experiment, which has just finished operating, has performed the first measurement using a method inspired by this one. But the Minerva experiment uses this type of detectors rather than this type of scintillator detectors, which means it has very coarse information about it can't actually determine the neutron kinetic energy on an event-by-event basis, but it can determine whether there was a neutron sometimes, and it can determine its direction. And they've been able to obtain a sample which is 20% pure in interactions of hydrogen. With the T2K near detector and its improved energy resolution, we can expect that this will reach about 60% purity with these small cubes. And if we also include longitudinal imbalances in addition to transverse imbalances, we can hope to get about 90% purity of interactions of hydrogen. So this is very promising for the future. Finally, we don't only have new detectors, we also have new analysis techniques. And one of them that I'd like to highlight is this prism style of measurements. So this consists in exploiting the fact that as we look at different off-axis angles, we actually probe different shapes of the neutrino flux. And this can be done in the same detector. So for instance, the SBND detector is so big compared and it is so close to the incoming BMB neutrino beam that even in the same detector, you could draw profiles of different off-axis angles and therefore sample different fluxes with the same detector. This can also be done with different detectors, and notably the T2K experiment recently published its first measurement using its near detector ND280, which is off-axis, but also its other near detector, which is Ingrid, which is on-axis, and soon will also include a third near detector at a different off-axis angle, which is Wagashi. So this is a very powerful technique which can help us reduce our systematics and probe the energy dependence of the way in which we model neutrino-nucleus interactions. And finally, we don't only need neutrinos to improve the modeling of neutrino interactions, we can also use other probes. And here I'd like to cite in particular electrons. So electron scattering and neutrino scattering are very analogous processes, and especially so with the exception of the axial part, the vector part is common to the two types of processes. So any theory that describes neutrino nucleus scattering must be able to also describe electron nucleus scattering. And for this, there will be new measurements with the class detector at JLab, and the E4New collaboration has produced a very important measurement, which was a very important analysis, which is published in Nature. So here, what they measure is the difference, so the energy transfer in the electrons in electron scattering processes. And this quantity is actually analogous to almost directly corresponds to the neutrino energy bias that I showed on the previous slide. And if you look here at the agreement between the models that we have in our generators and the experimental data, you can see that all of them fail to describe the actual energy bias that will impact dune analyses. So this is a very powerful probe for the future of neutrino oscillations. So to summarize, neutrino oscillation experiments are now entering the precision measurement era. This transition period between the start of Hyper-K and Dune in 2027 and 2031 is one in which the field really goes from one that is statistically limited to one of precision measurements. Our dominant source of systematic uncertainties are related to neutrino nucleus cross-sections, and our current results seem to hint that there might be CP violation in the lepton sector. The future experiments, Hyper-K and Dune, have very ambitious programs which hope to answer this question, but also to provide precision measurements of oscillation parameters, but they will rapidly be hindered by systematic uncertainties related to neutrino nucleus interactions. For this, fortunately, there is a global dedicated effort to improve our understanding of neutrino nucleus interactions, but there's also a significant analysis effort which needs to accompany it, and relies on a lot of iteration with the theory community as well in the process. There are exciting new measurements ahead, and I thank you for your attention.
Questions from the room? Yes.
Could you come back the Dune prism to build a totally brilliant architecture? And I thought this would give us some robustness to the devices. Is that true?
Yes. So it is entirely true that to some extent it will improve our robustness. I'll just explain what the Dune prism concept is. Dune prism is basically, so Dune will have 3 near detectors, 2 of which will be placed on rails, and they can just move perpendicular to the beam direction, which means that it can sample different off-axis angles, and therefore it can use then a linear combination, a precise linear combination of different off-axis angles to reconstruct the oscillated event spectrum. As a result, because it uses also the same target at the near detector, a lot of the systematics related to the neutrino flux and cross-section uncertainties cancel out. This comes with a caveat. One of the biggest, so it improves our robustness to the modeling of some effects, but not all of them. So there are still residual effects that we don't account for, some of them related to the beam geometry, and notably, it can't cover the entire beam spectrum. So for this, they'll need to take some separate runs with the flux in a bit of a different configuration just to make up for that missing phase space. The other thing that we sacrifice in this process is precision, because the result when we combine these different spectra, the statistical uncertainties from the linear combinations, notably due to negative coefficients, can actually become very big. They're not that big, not intendably big, but the truth is that it is less precise and the statistical errors are bigger than in the traditional analysis in which we constrain with just the near detector data. So it has a lot of potential. I think both of them are going to be done, but it depends on what your ultimate goal is. If it's the ultimate precision, and if you think we can improve our understanding of our models now, or whether it's just its robustness, and if that's enough for the goals of the experiment.
You mentioned this disagreement between NOvA and T2K, and you said that there was a group, but I think I've heard that, I don't know, 6-7 years ago, and it seems that very few progress has been done.
So I can say confidently that a lot of progress has been done. I'm on the review committee for this, and I know that the fit has been completed. In a few months, it will be published. I can't do
a global fit of two.
Yes, T2K and NOvA.
Which disagree so much?
They don't disagree that much, actually. So at this level of, so it looks a bit scary on this plot, but these are only 1 sigma intervals, and in reality, statistically, there's no real tension between the two. They're still compatible at the 1 sigma level. Yes, the 2 experiments have now brought together their 2 frameworks. They are doing a full joint fit, which is more than just a combination of statistical likelihoods, because via the variation of the oscillation parameters, the systematic parameters underlying each experiment can be varied at the same time. So it's a big step forward compared to the new fits, for instance, in which is just a combination of statistical likelihoods. But even there, only few parameters are still correlated due to a lot of technical difficulties. But yes, this has been going on for 6 or 7 years, and now is finally coming out in the next few months.
You don't know yet, so
I know the result, but I can't tell you. Yeah.
Other questions? I have a curiosity from somebody completely outside the field. So I'm from at the end we use very similar techniques. I'm from gamma-ray. So as you know, we have now a lot of pressure. I don't know how this from artificial intelligence.
Yeah.
And we have now a lot of push towards new analysis methods. I know that at CERN you are also at the forefront of this kind of thing. So what's the status in your field?
Oh, it depends a lot on what types of techniques. So I'm not a machine learning expert. I am starting to look into this right now. So one way in which machine learning and artificial, so there are several ways in which they can help us. One way of which I'm aware of, and that is heavily used, especially in the simulations for this new detector, the super FGD for the T2K new detector, is in pattern recognition in order to actually fit the tracks and also to predict the types of energy deposits that we have. So I think there's going to be a publication soon on the techniques that were developed for the reconstruction in this case. For Dune as well, there are many efforts to improve the reconstruction to help us with our fast simulations in liquid argon. Another way in which machine learning methods are useful, and that's something that I'm exploring right now, is we have a very highly dimensional fits. We have many parameters that vary at the same time, and we notably use. So we usually produce one simulation. A simulation is very costly. So every time we vary our systematic parameters, of which we have hundreds of or sometimes thousands, we can't produce a new simulation. So what we rely on is reweighting. When you can reweight exactly as a function of a variable that describes a physical process, then everything's great. When you have to reweight processes in which you've lost information along the way, such as hadron transport inside the nucleus is one example, there you actually rely on reweighting in 20 variables, for instance. And this is not something that can be approximated easily. And in this case, one thing that we can do is use, for instance, BDTs, boosted decision trees, in order to learn the features of 2 different, for instance, hadron transport models, and then perform multidimensional reweights in order to just have the weights or just the numbers at the end and not have to reproduce our simulations. So there are many interesting prospects in neutrino physics, and we're now just beginning to delve into them.
Thank you. Other questions? Okay, if on Zoom, no, besides a great talk. So thanks a lot. Thank you very much. Thank you very interesting. You can have a look at it.
Yes, please. You can just give me back my cubes.
Okay. Well,
Don't lose my cube.
This one I have one. Oh, go ahead.
Yeah?
Sorry. Yeah.
So just I saw the size of the cube and then also the image of flow. And I wondered what's the ratio of scintillator to fibers in this thing?
I don't know the number. So I mean, I can maybe if I sit down and write some geometry, I can work it out. But the size, so there are 3 fibers crossing each cube. Each fiber is 1 millimeter in diameter. So that's a cylinder of 1 centimeter times 1 millimeter diameter, 3 of those, and it's a 1 centimeter square cube.
They touch in the middle.
No, they don't. They are, if you see the cube, that you'll see that it's actually in a corner, so they don't intersect. And as a result, we have 2 million cubes in the super FGD, but we have only 60. Yeah, so we have like only 67,000 readout channels because of the fact that we have these. So we have 1 fiber crossing multiple cubes, so you don't actually end up with 2 million channels at the end. Yeah, thank you for your attention.